All right, this is page 10 of the notes packet. This is Lewis structures continued. So in my last video, things worked out for that Lewis structure. We had the perfect amount of electrons, we didn't have to do anything weird, it worked out. Fortunately, that's not going to be the case for every single set of atoms that you have. And so I'm going to show you two different scenarios that could occur for you. So I would take some time to read this section. I'm not going to waste your time reading it out loud to you. Instead, I'm going to be looking at these two. Okay? So, what happens if I run out of electrons? Okay? And this is referring to rule number 6 on page 9. So, let's say I'm dealing with HCN, hydrocyanic acid. Okay? Let's just start following that process for drawing a Lewis structure. So I'm going to count how many total valence electrons I have. I know that hydrogen has 1. I know that carbon has 4, and that nitrogen has 5. And when I add them all up, I get 10 electrons. So I remember that hydrogen is not allowed to be a central atom, okay, because it can only participate in one bond, okay? So I know the H has to go on the outside, which means my next one, carbon, is going to be in that center. Okay? And then finally I'm going to put N just over on the other side. Okay? And I'm going to bond them to the central atom to make this a molecule. And so in total I've drawn 4 electrons at this point. So we're going to look at hydrogen. Hydrogen's octet is filled. Hydrogen is weird. It only wants to have 2 electrons because of that first energy level. Okay, so hydrogen's chilling. Now I'm going to move on to nitrogen. Okay, nitrogen only has access to 2 valency electrons right now, but it wants 8 total. So I need to add 6 here. So lucky me, I still have 6. So I'm going to start drawing these. 1, 2, 3, 4, 5, 6. Okay, nitrogen's happy now, right? It has 2, 4, 6, 8 valence electrons. But here's the problem. We're going to go look at carbon. Carbon needs to follow the octet rule too. Everybody needs to be happy. If we're going to be shared, everybody needs to be happy. And so this raises some concerns. I'm not allowed to just poof add in extra electrons. I'm only allowed to deal with the money or the electrons that I have. Okay? So basically what's going to happen is nitrogen's going to say, hey, bro, I got you. Let me share with you. And he's just going to scoot his 2 electrons over to make a double bond there. Does nitrogen still have access to that? Yeah, he still has access to 2, 4, 6, 8 valence electrons, so he's still happy. He's just being a good friend. And if I take a look at carbon. Carbon now has access to 2, 4, 6 electrons, so he's almost there to his octet. But he's still not stable, he's still not happy. This isn't going to work unless he gets what he needs. Hydrogen can't help out here, right? Hydrogen is just sitting here with his 2 electrons. But nitrogen still has a couple lone pairs, so nitrogen's going to say, hey, I got you, bro. I'll just scoot my electrons over so we can share them. And when he does that, look, nitrogen still has access to 8 valence electrons, right? 2, 4, 6 in the middle right here, and then 2 on the right. So he's happy. He's stable. And I look at carbon, and look, carbon has 2, 4, 6, 8. He has access to 8, so he's happy too. And we have a total of 10 electrons, which is the only amount we were allowed to have anyways. So this would be a valid Lewis structure for HCN. Okay, so basically if you run out of electrons, you're going to start doubling up. You're going to start making double bonds. If you think about it this way, if you run out of rooms in your house for people, you start making bunk beds, right? All right, so now, what if I have too many electrons? Okay, I'm going to give you an example. This one's really weird and people are going to get freaked out by this, but you got to just trust. So, xenon tetrafluoride. This is an example of one of these where you have too many electrons. This is talking about step 7 on page 9. So here's what's going to happen. You're going to go ahead and total up all of your valence electrons. So xenon, I know this is weird, just trust. Xenon has 8 valence electrons. And then we have 4 fluorines, each with a total of 7 valence electrons, which brings us to 28 plus 8, which is 36 electrons that we have to account for. So xenon is allowed to have multiple bonds, so I'm going to put xenon in the middle. And I'm going to put those 4 fluorines around him. Okay? And in order to make this molecule, I got to draw those little bonds happening. And that's 2, 4, 6, 8 total electrons right there that I just drew. So now I have 28 left that I'm allowed to deal with. Once again, I'm going to go ahead and start filling those octets for the outer atoms. So I'm going to say 1, 2, 3, 4, 5, 6, and then 7, 8, right? So that's 22 left. And then 1, 2, 3, 4, 5, 6, 7, 8. That's 16 left. 1, 2, 3, 4, 5, 6, 7, 8. 10 left. 1, 2, 3, 4, 5, 6. Okay, look at my fluorines. Are all my fluorines chilling? Are they pretty stable? Yeah, they got a full octet. Every single one of them has access to 8 electrons. So now I need to go look at xenon. Does xenon have his full octet? Yeah, he does. He has 8 electrons that he has access to. So are we done? No, we still have 4 electrons we have to deal with. We need to be responsible accountants here, okay? So where do we put those extra electrons? Here's what you're going to do. It feels weird, but you just got to do it. We'll talk about it later, okay? You're going to add those 4 extra electrons in as lone pairs around xenon. Isn't that weird? Okay, that's just what you do. If you have extra electrons, you put it on that central atom. It is more stable to put those extra electrons on the central atom. And so in this case, xenon actually has access to 2, 4, 6, 8, 10, 12 electrons, which is really weird. Okay, but there's an example of what you would do. You just shove those on as lone pairs onto that central atom.